So I want to start out by showing you a little bit about the structure of numbers that explains why we do things the way we do them. And I know it's going to be a little bit laid back for some of you today because you know what we're doing, but I urge you to at least pay attention to what I'm saying so you can maybe see some of the nuances behind why you've done these processes. So even if you're really good with operations with numbers, there's still a benefit to seeing some of this. The biggest thing, probably the simplest topic in math, and also probably the most misunderstood topic in math, right from the very beginning, is the idea of what is a number. Now, most people look at that and think, geez, I know what a number is. I don't need a lesson on that, especially not in college. I were to put 4 up here. How many of you, just a show of hands, would tell me that that's a number? Most of you would. A couple of you got your hands down, so he's not asking that question because he wouldn't ask me if there wasn't a trick to it, right? Well, 4 is what most people would refer to as a number, but it's just a numeral. It's an amount. To really be a number, there are 2 parts to it, and the second part's actually hidden within that 4, and we're going to learn about that in a little while. But a true number has 2 parts. It has the amount, the 4, but it also tells us what it is. We might have 4 cows. Since we're in northern Wisconsin, we'll go with the agricultural theme. Now that is truly a number. It tells us an amount. It tells us how many, which I'm going to call the count. We have 4 of something. And then it also has what it is that we're counting, which I'm going to refer to as the name. We have 4 cows. Then you might be sitting there looking at that thinking, why am I sitting in a college class talking about 4 cows and the parts of a number? Well, because when we do operations, there's some very significant consequences of those 2 parts of the numbers that we often don't see. So let's look at our 2 most basic math operations, addition and multiplication. A couple of you probably just twitched a little bit there. It's like, wait a second, where'd subtraction go? I thought those were the 2 simplest, addition and subtraction. Well, addition and subtraction are technically the same operation, just going in forward and reverse. So pretty much all of the rules and explanations that apply to addition also apply to subtraction. In fact, when we talk about negative numbers, you're going to find out that subtraction really is just a specialized form of addition. And the same goes for multiplication and division. Multiplication and division are really one operation, just one is going forward and the other one's going in reverse. In fact, the definition of division is defined through a related multiplication problem. So anyway, let's look at an example. Since you guys are in construction, let's use some dimensions here. So let's take 4 inches plus 7 inches. What do you get? 11 what? Inches. Not a terribly tough problem, but let's look at what happened in terms of our count and our name. So we have our counts, our 4 and our 7. What happened to those? Well, we combined them to make 11, right? So we combined our counts. Let's look at the names. We had inches, and it became inches. It just stayed the same. We ended up keeping the same name. So when we add numbers, we combine the counts and we keep the same name. Now that doesn't sound like earth-shattering information, right? Probably not quite worth your $400 for the course yet. But if we look at multiplication, there's a significant difference. I'm going to abbreviate inches with IN. I should probably put the right symbol in there. Are all of you familiar with the dot for multiplication instead of the X? It means the same thing. It's just when we start talking about variables later, it's less confusing. So if I have 4 inches times 7 inches, what do I have? 28 what? Not inches anymore, but inches squared, or square inches. So what happened here, we had our counts, the 4 and the 7, and what happened to them? Well, we multiply them. They combined the 4 and the 7 to make 28. So we still combine the counts. It's just this time we combine them with multiplication instead of addition, because that's the operation we're using. But the significant difference comes in the names. What happened with the names? We had inches and inches, and we got inches squared. When we multiply, we also combine the names. That is a huge difference. Now, it may not look like much, but it really is. The fact that when we add, we keep the same name, and that when we multiply, we combine the names, has big consequences on the rules for how we do those operations. In fact, it even will define for us what numbers we can use in each operation. For example, let's say I have 5 cows and 3 boys. Does that give us 8 cowboys? No. Or if I switch it around, but I had 3 boys and 5 cows, that'll give us 8 boy cows. Any farm kids in here? The farmers? You can tell me that is a whole bunch of bull. I know, a long way to go for a joke. I'm a math teacher, so I'm required by law to have a really stupid sense of humor. You'll get used to it. The point of it is, long way to go to make a small point is, when we add numbers, because we're going to keep the same name, we must start out with the same name. We cannot add cows and boys because they don't have the same name. We're going to add inches and inches because we're just going to keep that name to be inches. You can't keep the same name unless you have the same name. Multiplication, however, you don't have to because we're going to combine the names. For example, let's look at let's say I have 3 feet plus 7 pounds. Can I add those? No, they have different names. 3 feet plus 7 pounds is just 3 feet plus 7 pounds. I can't do anything more with it. But for multiplication, 3 feet times 7 pounds. Well, I'm going to combine the counts. What's 3 times 7? 21. And then I'm also going to combine the names. What's feet times pounds? Foot-pounds, which is a unit of torque or moment. When I multiply, I don't need the same name because I'm just going to combine the names. Has some very serious consequences when we get into our other forms of numbers as well. Let's talk for a little while about everybody's favorite type of number, the fraction. What does it mean to have 3 sevenths? Now, I realize I'm just kidding there. If I asked most people on their way in the door what they hated most about math, 4 out of 5 people would say fractions. The other one would probably say the teacher. Little review, what's the top number of the fraction? Numerator, very good. Bottom number? Denominator. Looking at those words, it's probably a good time to also point out that I sometimes have very poor handwriting. I also am not a great speller. So if anything ever appears up on the board that you can't read or don't recognize, I assure you it was intended to be English, but I may have just horribly misspelled it or wrote it so sloppy you can't read it. I will never be offended if you ask me what something says. I'll erase it and rewrite it for you if I need to. So anyway, let's look at those 2 words. To numerate. An example of numerating. Every 10 years, our government sends out people to do the census, and they're being asked to numerate the population. What are they doing? They're counting. The numerator is a count. Well, at this point, you can probably guess what the denominator is. To denominate means to classify. We have different denominations of money, different denominations of religious organizations. To denominate means to classify or to give a name. So denominator is a name. So a fraction, when we look at a fraction, most of us see 2 numbers, a 3 and a 7 in this case. But it really isn't. It is a single number with 2 parts, because every number has 2 parts. It has the count and the name. And when we go to do operations with those numbers, those 2 parts interact just like they would with any other type of number. Let's take 3 sevenths plus 2 sevenths. First of all, somewhere around 3rd or 4th grade, our teacher told us that when you add fractions, you must have common denominator. Not just because your teacher said so, but because when we add numbers, any type of numbers, we must have the same name. So with fractions, having that common denominator to add or subtract is nothing new. It's just like any other form of number, we must have the same name. That same teacher then told us, what do you do to add those fractions? Perfect. You add the numerators. 3 plus 2 is 5. And you keep the denominator. Keep that common denominator of 7. Well, that's, again, nothing new for fractions. It's because that's how we add all numbers. You combine the counts and you keep the same name. If we have something like 1/4 plus 2/3, can we add those the way they're written? No. Now, when we talk more about fractions, we'll talk about how do you change their name so that you can add them. But for right now, we're just going to leave it, hey, they don't have the same name. You can't add them in that form. On the other side, for multiplication, however, 3/7 times 2/7, that same 3rd or 4th grade teacher taught us to do what when we multiplied? Now, multiply straight across. Right? 3 times 2 is 6. 7 times 7 is 49. Again, that's nothing special. There's no special rule for fractions. That's how we multiply all numbers, no matter what form they're in, is you combine the counts, 3 times 2. And you also combine the names, 7 times 7. And let's look at our 1/4 times 2/3. Again, we don't need a common denominator to multiply because when we multiply, we do not need the same name as we saw up here. We're just going to combine the counts. 1 plus 2 is, or 1 times 2, I should say, 2. And 4 times 3 is 12. Now, a lot of you probably look at that and realize you can reduce that, and we can. We're just, when we get to fractions in more detail, we'll talk about reducing those. So you can see here, everything we've learned about fractions, those operations, we've learned that there's special rules for fractions. There really isn't. It is the same rules that apply to whole numbers. They just look different because fractions look different. Well, let's look at another form of number. A decimal, 0.21. Well, what's the formal way of pronouncing that? Not just 0.21, but we would say what? Yeah, there we go, 21 hundredths. And when we write it out that way, it's really obvious to see where is the count and where is the name. So let's look at operations with decimals. Let's try to add some decimals. If I had, let's say, 0.21 plus 0.3. If I go to add those, is that going to work? It should? What's wrong with it? What's wrong? Okay, yeah, we've always been told that we have to do what when we add and subtract decimals? Line up those decimal points. We got to move this over so that decimal point's lined up. Why? 3rd grade teacher said so, huh? Yeah, this is 21 hundredths. This is actually 3 tenths. They have different names. Fortunately, if we just put a 0 there, now that becomes, instead of 3 tenths, it is 30 hundredths. So now they're the same name. And if we have that 0 in there, the decimal points automatically line up. And when we add them, 1 plus 0 is 1, 3 plus 2 is 5. What do we do with the decimal point? Move straight down. Again, that's not a special rule for decimals. When we add numbers or subtract numbers, we keep the same name. Moving that decimal point straight down is just keeping the same name. How about multiplying? If I do 0.21 times 0.3, do I have to line up the decimal points? No, we don't. Because when we multiply, we do not need the same name. Well, 21 times 3 is 63. Where's my decimal point going to go? Put a 0 and then the decimal point. Why? We were taught by that same 3rd or 4th grade teacher. We put a lot of faith in what they told us, didn't we? You count 1, 2, 3 decimal places in the problem. So then you got to count backwards 1, 2, 3 decimal places in the answer. Correct? Why is that true, though? Again, it's not just because they told us so. It's because this is 21 hundredths. And this is 3 thousandths. And when we multiply, we combine counts. 21 times 3 is 63. But we also combine the names. Hundredths times thousands. Did I say thousandths? Why did I say thousands? That's actually 3 what? Tenths. Okay. You guys got to stay awake because some days I'm not. That's tenths. Sorry. Hopefully I didn't confuse you. Hundredths times tenths is, that would be the thousandths. Some days my mind gets ahead of my mouth gets ahead of my mind. So you can see, counting those decimal places in the problem and making sure we have that many decimal places in the answer is nothing more than combining the names. Let's look at some other forms of numbers just for fun. Let's look at that, 5x, an algebraic number. Now, a lot of people start to get a little nervous when they see that. They don't like having letters in with the numbers. The algebra is where most people start to struggle. But again, as long as we see the rules for dealing with whole numbers, the rules for algebraic numbers are exactly the same. Once again, we have 2 parts here. We have the count, which is the 5, and we have the name, which is the x. And that 5x behaves exactly the same way as 5 inches or 5 cows or 5 sevenths would behave. The difference is we know what an inch is. We just don't necessarily know what an x is. But it really doesn't matter. If I have 5x plus 9x, what am I going to get? Now we combine the counts. 5 plus 9 is 14, and we keep the same name, x. Just like 5 inches and 9 inches would be 14 inches. What if I had 7x plus 2y? What do I get? Exactly. Just like when we added feet and pounds, we ended up with feet and pounds. Same here. 7x plus 2y just stays 7x plus 2y. We cannot combine them with division or with addition or subtraction because they have different names. On the other side, for multiplication, 5x times 9x is going to become 45. 5 times 9 is 45. Yeah, and just like inches times inches became inches squared, x times x becomes x squared. What about our 7x times a 2y? Can we do it? Yeah, we can do it because we don't need the same name to multiply. And yeah, it's the same process. Combine the counts. 7 times 2 is 14. And just like feet times pounds became foot pounds, x times y becomes xy. It's just that simple. Erase here. Come on. We're not going to work a lot with scientific notation, but the same rules apply in scientific notation. The difference is in scientific notation, the name is our power of 10. So if we go to add numbers in scientific notation, 3.2 times 10 to the third plus 5.1 times 10 to the third. They must have the same name to add or subtract, which means they must have that same power of 10. And just like any other addition, we add the counts. 3.2 plus 5.1 is 8.3. And we keep the same name. It's going to still be 10 to the third. However, when we multiply, I can have 3.4 times 10 to the 8th times 2.1 times 10 to the 5th. We do not need the same name. We're just going to combine the counts. 3.4 times 2.1 is, anybody? What's that? Careful. 7.14. Okay. Somebody want to double check me? Here, I'll do it. Oops, 7.35. Holy cow, I was off. Oh, let's go to 3.4, not 3.5. I was going to say, any better. Yeah, it is. 7.14. Perfect. So we multiplied the counts. Now we also multiply the names. 10.8 times 10.5. Now, it'll be a couple weeks before we look at rules of exponents. I wouldn't expect you to know this now necessarily. But 10 to the 8th times 10 to the 5th is 10 to the 13th. We also combine the names. I just went through a lot of stuff in about 25 minutes, and I realized that. All of this stuff is pretty much stuff we're going to go back and we're going to look at in more detail over the next couple of weeks. So if any of this is confusing to you, don't feel bad. We're going to see it again. But I want to throw it all there all at once like this at the beginning, just so you can see that there are just this couple underlying rules in math that if you understand those rules, everything else fits into place. We're going to take our break here in just a second, and when we come back, we'll actually start looking at the operations with whole numbers in more detail and how all this stuff applies to those. Because I realize what we did here doesn't look a whole lot like what you usually do when you're dealing with numbers. So we'll start looking at how does that fit into it. So let's take our break. It is 1:15 right now, so let's come back at 1:25 and we will start up again.